All right, hello AP Physics, Mr. Martineau again. Marty here to serve you as a humble servant of science. So anyhow, we are now on video 3 of concave mirrors. If you missed videos 1 and 2, you need to do them first, and you definitely need to see video 1 because the setup of my paper here has already been determined, so we're not going to take time to do that. If you don't remember how to do that, please go back to video 1 and set it up properly. Once again, I have my curved mirror. It is concave. I have set up the usual... Sound like Bob Ross. I'm going to run the colors in the bottom. 10 centimeter center of curvature, 5 centimeter focal length. I am now placing an object at 2.5 centimeters from my mirror. So we're putting it in front of the focal point, and my object is again going to be 3 centimeters high. So if I come back over here, I already measured it out. Okay, this distance is 2.5 centimeters. I already measured it. That arrow is 3 centimeters tall, just like the last drawing. However, please note, my center of curvature, in the last 2 diagrams, the center of curvature I kind of eyeballed in the middle of the paper. This one I shifted over to the left. The radius is still the same, it's still 10 centimeters, but I'm going to need some room, so I moved it over, and you'll find out why in a minute. This begs the question, as I mentioned in the first video, when you're looking at a concave mirror and you're standing in front of it, you first see yourself, depending where you are, you'll see yourself right side up and magnified, then you'll see nothing, and then you'll see yourself upside down. So in the first case, we saw an upside down image. In the second video, we saw no image. So this must be the third image. And what's really interesting is, depending where you are, you get a different image. And it's because how the light rays come together. And as long as those light rays are following the ray model of light, and we're establishing that an image can be made with 3 rays, we're going to get this kind of odd relationship. And I'm out of focus, and I don't know. Well, there we go. Yep. Okay, super. So let's begin. Now, your job is to draw this, and then you're going to go after and make your measurements. So I'm expecting as neat a diagram as I'm making. Okay, let's go back to those 3 rays. First ray, parallel to the axis through the focus. So I'm going back to the tip of my arrow again. I'm going to try to make this as parallel as I can. The ray is going in, parallel to the axis, and then it's going to bounce back and go through the focal point just like that. And put some arrows on it so that I know which one is coming in and which one's reflected. That's going to be ray 1 and ray 1. There you go. Cool? All right, now no tricks here. We're going to go through the focus parallel to the axis. Gets a little weird. Again, please pause it, go in slow motion, rewind it, make sure you get it right before you commit pen to paper. Next one goes through the focus parallel to the axis. Here's how this works. You line up your arrowhead with the focal point. You're going to use that as a guide because the ray isn't going to go backwards, it's going to go forwards. What I'm going to do here is I'm going to put a little dotted line. This does not represent an actual ray of light. It's just going to represent a guide because this light ray that's going to come off the arrowhead is going forward to the mirror. So we're using my dotted line as a guide. This does not represent an actual ray. This is actually a virtual ray. This is the actual ray. And then it's going to bounce back parallel to the axis. Like that. And this is ray number 2. Okay, sorry, there's a little bit of a traffic jam here of numbers, but you get the idea. That's ray 1, that's ray 2. Again, at this moment, students usually go, what, wait? So please feel free to pause the video and make sure that you've drawn it properly. Okay, super. Don't be afraid of that. All right, third ray is going through the center of curvature and not bouncing and bouncing straight back. So once again, tip of the arrow. Going to line up my ruler with the center of curvature. It's over here. Here's my tip of my arrow. Once again, we're going straight up. It's going to bounce straight back and go through the center of curvature. Here's ray number 3. Bit of a traffic jam of numbers. Now, this is curious. Let's take a look over here. These rays are never coming together. This one's going off at an angle, that one's going off on an angle, that one's going off on an angle. So these rays are never going to come together. So how can we make an image? If you remember from planar mirrors, when we did that experiment, those rays never came together either, but yet we see something in the mirror. So what's going on? Here's what we got to do. We have to extend virtual rays back behind the mirror. So we're going to go to ray 1. here's ray 1. Here's the reflected ray of ray 1. See? Okay, so here's ray 1. And what we're going to do is we're going to extend this ray backwards with a virtual ray. So this is virtual ray number 1. Let's go to ray number 2. Okay, ray number 2 is this one that went this way and back that way. So what I'm going to do is I'm going to line up my ruler with the reflected ray for ray number 2. Can you move the camera over that way? See, there's ray number 2. Again, I'm lining it up with the reflected ray of 2, and I'm going to draw that virtual ray backwards as well. And if you notice, we seem like we have a pattern here. Looks like rays are going to intersect right about there. Now, the third ray is the pièce de résistance. I said that wrong. Pièce de résistance. Third ray. Check this out. And I think people like this because of the, like, kids that dig on the symmetry and just like patterns. There's a neat pattern here. So here's my third ray, right? So now that's my third reflected ray. I'm going to draw that ray back behind the mirror. And look what happens. Now again, a little bit of error. It's not the end of the world.
Do you want to label those 2 and 3?
Yeah, I should. Thank you for that. This was 3 and this was 2. So again, all of my, if you remember from the first diagram, we are recreating the tip of the arrow where the rays come together. That's about right there. I'm going to draw an arrowhead. I'm going to make it dotted just to kind of hammer the point home that this is a virtual, oops, I gave it away. Well, too late now. It is a virtual image. Real rays did not come together to make this. Okay, next thing, we're going to measure this distance. I get about 1.7 centimeters. So this is 1.7 centimeters. Now, I want to pan out a bit. Please remember from other videos that we don't expect to see light on this side of the mirror. This is concave this way. So light doesn't belong behind here because light doesn't go through a mirror, but here's our image. So please remember that makes this a negative. Anything from this point on this side is a negative distance. Anything from this point on that side is a positive distance. Now what your job is that you need to go to your drawing and you need to measure HI, what's the height of the image. You have to measure DI. Don't use my 1.7 because you probably have something different. Come to the bottom. So you're going to record that here as well. You're going to calculate the focal point, just like video 1, using the mirror formula, 1 over F equals 1 over DO plus 1 over DI. But be careful of the signs on your DO and DI, and make sure that you're actually calculating F. Again, F is 5 centimeters. You're going to calculate your magnification. The formula is on video number 1. Is this image real or virtual? I kind of gave that away. Is the image upright or inverted? Pan out. So if you can do all that for me and you have a diagram that looks like this, you'll upload it to your document, and that is the next drawing. Thanks again, and good luck.